Hello everyone, and welcome in this new recording. Today I would like to talk about the Mipmap generation process which you can use when you're working with WebGPU. Lately I've been working pretty hard actually on the implementation of the ocean rendering on my NervLand project. And this is the main class that I have to do the ocean rendering process. And at some point, I need to generate some mipmaps for a given texture. The point is, in WebGPU, you don't have a dedicated routine to compute the mipmaps. So you basically have to do it yourself, and you will find some resources online. The main one I think is this page, which is trying to explain how you can do the mipmap generation using a compute shader. So this is in fact what I've used as a starting point myself, but all the code that is mentioned here is not really what I'm going to use directly because yeah, I'm using my own engine, so it's basically encapsulating all those details. But anyway, the idea is really the same thing as what we have here. And as a side note, actually, there is this other page here which is about generation of mipmaps with WebGPU, and it's still open, so there is a lot of discussion going on. As you can see here, it's indicating that yes, we have support for generating mipmaps directly in WebGL. I guess it's also the same if you use OpenGL directly, but not really in those higher level APIs, or maybe yeah, in Metal you have something, but it doesn't seem to be the case for DirectX 12 or Vulkan. So first let's have a look at the unit tests which I have prepared to test this feature. Basically we have two tests in there. This is the first one, which is considering the mipmap generation for a simple 2D texture and RGBA 2D texture with a float32 format. What we're going to do here is first we're going to prepare the size that we want for the test texture here. So it's 128 by 64 pixels, and we're going to generate random float values, keeping in mind that we need 4 channels per pixel. And we calculate the number of mipmaps that we need for this size of the texture. So we have a dedicated function for that. So this is a known formula, I guess, just using the log2 to compute the maximum mipmap level. And after that, we're going to create the GPU texture, allocating the data directly. So uploading the data for the level 0 of the texture directly on the GPU. After that, I'm going to call this key function that I have implemented to generate mipmaps, which is simply taking the texture as input and filling all the mipmap levels in the texture. Because what you need to also keep in mind is when you're creating the texture here, you need to specify the number of mipmaps level that you want to have for this object. But all the levels except the level 0 are going to be just empty initially. After that, I'm going to use this custom function here in C++, which is going to generate all the mipmaps on the CPU side. We can have a quick look at that. It's a bit tricky, so I don't want to get into the details, but really what you're going to do is you take one level, and for this level you're going to consider those 4 pixels that you have next to another and compute the mean value. So this is done in this loop, and the result is going to be stored in the next level. This function also supports dealing with multiple layers. So in case you have a texture 2D array, you can specify the number of layers that you have in your array here, and it's going to compute the mipmap levels for each of those layers. Okay, and after that, when we're done preparing the CPU data that will be used as reference data, we are simply going to iterate on all those mipmap levels, and every time we're going to download from the GPU the data corresponding to this specific level from the texture that we created initially. So that's going to fill this GPU data array. We're going to retrieve the CPU data corresponding to that level, and we're going to simply compare all the float values one after another in this loop. And that's it. This is the unit test that I've created to test this generate mipmap functions, and it's working just fine. I also implemented another unit test, in fact, to test the array version of it, because in this case, you see, we're going to start with the same kind of texture setting, except we're going to also have 10 layers for our texture 2D array. Next, we're going to create a texture 2D array instead of simple texture 2D. But the function we're going to call here is still the same, generate mipmaps. And next we keep going, generating the level data on the CPU side and comparing once again all the data for a given level. When we call this, it's going to retrieve all the data for all the layers at that level. So when you do the comparison here, all the layers are considered. So now let's have a look at this generate mipmaps function. So in there, we are first going to do a simple check here, because you can call this function in two ways. Either you're not specifying any kind of compute path. In this case, you're going to create one on its own, generate some mipmaps using this compute path and executing this compute path immediately. So that's if you want to do the mipmap generation immediately, basically. Otherwise, you can also integrate this mipmap generation step in another existing compute path. So you would provide this existing compute path directly, and this would get you to this point. Starting from here, you're going to just check, in fact, if you're dealing with a texture 2D or a texture 2D array, depending on the number of layers that you have. And if we have a texture 2D array, we actually need to do things pretty differently in the shader code itself. So that's why we have this definition here, is text 2D array, which is going to basically change all the logic in the shader that we will see in a moment. In addition to that, the thing with this mipmap generation process is that you're going to have to write to a given texture level, which means that since we're using a compute shader here, we're going to use storage texture, and to write to it, you need to specify what is the format of the pixels for those for this texture storage. So depending on the format that you have here, you need to provide another definition to the shader, and we'll see also in a moment where this is used exactly. So this means that if I need to deal with additional format, I will need to extend this switch here. And next we have this part, which is the interesting part, where you're going to do the generation one level after another. What's happening here is you're going to create a binding group, and for this binding group you will provide the texture that you're dealing with, but only provide the level -1 level and all the layers in case it's a texture 2D array. So this is where you're going to read your data from, and that's the previous level. Then you also need to provide the destination where you're going to do the storage. So you provide a storage texture, which is still the same texture, but this time you're going to provide the level itself and still provide all the layers. And that's an interesting usage case, because what you're doing here is you're really providing the same texture but different texture views on that texture. There's a first view here which is created on the level -1, which is going to be a texture where you are going to read from, and then you have another view here which is the storage 2D texture where you're going to write the data. And this is fine because the two views are on separated data from the same texture, so you can read from somewhere and write somewhere else in the same texture at the same time. This is legit. And once you have created your binding group like that, you just add the work here in your compute node. And another interesting trick I think I should mention here is this part. Here you're basically defining what is the size of the grid of work group that you have, assuming that for each work group you have 8x8 threads. And as you can see here, for the width of this grid, we're using the width of the level that you're considering from the texture multiplied by the number of layers. Why that? Because the shader itself is going to do the mipmap computation on all layers at the same time for a given level. So you can imagine that you have all the layer images stacked horizontally, one next to another, into the compute grid. And then each thread on the GPU side is going to figure out what is the current layer that you want to consider given the global invocation index of that thread. So we'll see a bit more of this trick when we look at the shader code itself. And I guess, yeah, basically this is it. After that, when you're done registering all the compute step, you simply add this compute node to the compute path. Now let's have a look at the actual shader itself, generate Mipmap shader. So as I said on that part, depending on whether you're dealing with a texture 2D array or simple texture 2D, you're going to behave largely differently. So as you can see, the inputs that you receive is already different. We can have a texture 2D array in this case and texture storage 2D array also, and otherwise it's a simple texture 2D. As I said, we also need to take care of this output format, which will depend on the format of the texture that you are providing. So this is a dynamic part of the code. And these are the only two entries that you really need in both cases. The source texture, which is more the source level of your texture, and then the destination level of the same texture. Next, we have this main function. First thing we need to do is to figure out what is the current dimension for your destination texture. And keep in mind that when you're talking about destination texture here, you're really talking about texture views. So the dimension that you will get here are the dimension of the view that you provided as an input for the shader. So it's going to change depending on what is the current level. It's going to reduce progressively and give you the dimension for the current level that you want to generate, because that's the destination part. Next, as I said, we proceed completely differently whether it's a 2D array or not. So let's have a look at the regular texture 2D path for a start. In that part, first you really need to check if you are still on the texture or not, because if your invocation index is outside of the texture, you don't have to do anything. And that is just going to give you your pixel X and Y coordinates from those invocation coordinates. Next, this is also an important part when you have to do this Mipmap generation, which makes me think that if you look at here, I don't seem to have this in place. So yeah, I think this algorithm here is only really going to work for square textures that are powers of 2 in dimensions, but not in a generic case, because what's going to happen is, in some cases, if you have a rectangle texture, for instance, you will eventually reach a level where, for instance, you could say on the width there's only 1 pixel left for your texture, and on the height of the texture you still have like 8 or 4 or more pixels, and you're still going to reduce the 8 value. So if you have 8 pixels, you're going to generate the next Mipmap level with 4 pixels, but you will still have just 1 pixel on the width of the texture. So there is you cannot assume that when you are at a given level, the parent level will have 2 times more pixels in a given dimension. It could also have just the same number of pixels, which would be 1. So that's why you need to figure out what is the dimension of your source texture here. Remove 1 so that you have a pixel number going from 0 to size -1. And then when you're going to do the sampling from the source, you use the theoretical coordinates of the source point, so 2 times what is your current level coordinates, but you take the min with the size, because you don't want to get outside of the bounds of your source texture. So yeah, bit tricky, but if you don't do that, the generation is not producing the proper result, because I think when you get outside of the texture, it's returning 0, and that not matching what you would get on the CPU side otherwise. So this is important to keep in, I believe. And then this part is basically the core of the algorithm. You're going to sample the 4 coordinates next to one another and compute the mean value, and that's what you're going to store in the destination texture for the current level coordinates. Next, in the case of the texture array, it's slightly more complex, but not that much if you think about it. You only really need to figure out what are the number of layers that you have for this destination level. And as I said, for the x coordinate of the grid, you need to figure out if this is bigger than the width of your texture multiply by the number of layers, because we are stacking those layers on the width dimension. And next, you cannot really use this invocation ID x as your current pixel x coordinate. What you need to do first is to figure out what is the current layer. So you divide this by the width that you have for your texture, and next your pixel coordinate is going to be this x value minus layer times the width of the texture. And from that point, you keep doing the same thing as before. We're going to still use this source size, taking the mean between the coordinate, the theoretical coordinate, and the source size. And next we need to do the sampling from a specific layer. Another thing I didn't really mention is, as you can see here, we're sampling from the level 0 of the texture. And that's because for the view that we are attaching, whatever is the current level that you have attached. So here, for instance, you see I could be attaching level 3, but from the shader perspective, what we call level 3 is simply what we are going to use as level 0 in the view. It's the only level that we are providing. It's the first one, so that's level 0. So those indices here, and also here in fact, are relative to the view that you're providing in your binding group. And I think this was mentioned also in the article here. You see that when you do the sampling here, they are also using 0, and that's because the last argument here is a Mipmap level relative to the texture view that was bound. And so yeah, this is it. We continue after that, computing the mean color and storing the result in the given layer. Now, just to quickly show you that this is working fine, I'm going to run those unit tests here, which is going to execute the 2 tests that we mentioned initially. And yeah, we're going to compare all the Mipmap levels, and it's working just fine with no error. So this is it, guys. I hope you learned something. The thing is, you probably can adapt this algorithm to DirectX 12 or Vulkan directly. But yeah, it's also not the absolute best solution that we can provide, because what I'm doing here is that we're going to process the levels one by one, which means that for each level we're going to read the data from the previous level. So that's a texture read from the previous level in the shader. So all those reads that we're doing here. What we could do instead would be to read the data from a given level and store that in the shared memory of your work group, and then use this shared data to generate multiple levels at the same time. So you're going to write maybe 2, 3, or 4 levels in a single pass instead of rendering the levels one by one. So that could be a bit more efficient, but it's a bit more tricky to implement. So maybe I get to this another time, but for the moment I just wanted to have a simple implementation, and this is doing the job just fine. So yeah, thank you very much for watching. As usual, if you have any question, let me know in the comments, and otherwise, see you next time. Bye bye.